Morning, we're looking specifically at the scientific method. Now, this is what I will be covering in day one of my class, so you know exactly what to expect. Scientific method is where every good science class should start. Scientific method is a systematic approach to solving a problem. So if we have a problem, we need to have a way of looking at it. Now, in order to have that, you have to have steps. Now, the first step in the scientific method is to identify a problem. We need to be looking at problems, identifying what they are, and going from there. Now, once we do that, second step is we make observations. Now, when we make observation, we use our senses. We use our sight, our hearing, smell. When you smell things in chemistry, you never put it directly in our nose. You wave it towards yourself to properly identify. You do background reference. You make sure you get as much information you can to get a good understanding, and we're going to form a hypothesis. Now, hypothesis is a Greek word. It means an educated guess. Now, I have a line here because this process has been going on for a long time. The first group to do that were the Greeks. But the problem is they never went any further. Once they identified a problem, they considered a fact. There were scientists like Democritus. Democritus identified that an atom, or atmos, indivisible in Greek, was the smallest particle of matter, which was a good thing. But he never went any further, and he could only look at what he had because he couldn't see a proton, a neutron, and an electron, which we know today make up atoms. So he just looked around and saw fire, found earth. So he thought there were four things: earth, wind, fire, water, which made up atoms. Never went any further, and that was considered a fact. Again, they made some good decisions. Sometimes they made some, rather bonehead decisions. One of the examples, if you've ever known somebody that gets really, really angry, their face turns red. Also, if you've ever been camping before and stand too close to the fire, your face turns red. So if a fire makes your face turn red, people that get angry have fire red in their face. Greeks believed that people that got angry all the time had fire in their head. He's a hothead. That's where that expression came from. Now, we unfortunately today, for some people, we go further, we test. Now, testing is a very important part of scientific method. When you test, you have to have control groups. So these are called variables. The independent variable is the one that we control. The dependent variable is the one that's generated from it. And the controls are where we remove certain things to make sure that it's actually causing that factor to be true. If I were to come up with a drug that I think is a possible cure, what I do is I bring in a drug study, and I would give some of the people in the drug study my miracle cure drug. And if they get healed and they get better, well, then that's what it is. But I also, to make sure it's just not positive thinking or hope or faith that's actually making them better, so I give them a sugar cube, what we call the placebo. Now, if the people that are taking my drug get better, then it's a true test. If also then the people that aren't taking it don't get better, then it's probably also accurate. So that's what a control is. Remove that factor that we're testing. We also have to have a large group size. Now, this is something you'd be very careful when you're looking at research studies. I have seen studies with 50, 20, 100 people. From everything that I've seen, that's not really enough. In order to have a reliable study, you need to have at least 1,000 people to be considered effective. That will take out any possibility of chance. We also need to have diverse sampling, so people from different ethnicities, different economic backgrounds, different cultural backgrounds, different ways to make sure that those factors don't control it. We also have to have some kind of randomness. We have to make sure that we don't pick our samples to purposely obtain our information. When we do all this, we're going to get results. Now, results are neither good nor bad. They're just numbers, okay? So don't ever think that results by themselves give us value. We have to evaluate. Now, when we evaluate, there's two possibilities. We can be true and right, which we're going to go forward. But if we're wrong, what we're going to do, we're going to go all the way back up to making more observations. We're going to start over again, form a new hypothesis, create a test with a control group, large sample size, diverse, random, get results. If I'm wrong, going back up again. Observe, new hypothesis, test. We can do this in the scientific method. 5, 10, 15, 20 years even, keep going over and over and over. Now, if I get a really good process and actually proves to be right, there's two possibilities. I can get a theory or a law. Now, theory and law aren't the same thing. Definition of a theory is the best explanation for a problem. Okay? Examples of theories would be evolution and creation. Evolution, from goo to you through the zoo. Okay, that's one way that some people look at it. Creation or design theory says that there was a person or a thing that ordered things, God, and made it work. Now, because neither of those things have been seen, we've never seen an evolutionary change, we've not seen creation, and they're not very repeatable. Now, adaptations, that's acceptable. Evolution, I'm not so sure. Okay, in fact, I'm not sure. I don't think it's true. Law, on the other hand, is a belief we assume to be true. Now, we say assumed as opposed to actually being considered true. Always the case. Gravity is an example of a law. A law works everywhere. If you take the top of a building, push you off, you're going to go straight down and go splat. But does it work everywhere? Well, there is one place, deep space, called black holes. Now, black holes, we believe, are collapsed stars, intense gravitational field. Nothing, including light, gets out of it. That's why they're black. Now, we don't know why, but for some reason, a radio wave shoots out the middle of a black hole. Should that happen? No. Is gravity still a law? Yes. Assumed to be true, not necessarily directly true. Now, I'm going to show you a little experiment here to sort of demonstrate. I do this in class with my kids. I grabbed my son, Seth, and that's Seth right there to help me out, and we'll do a little explanation of what's going on here.
With a glass of water.
So we have water right there, just pure tap water.
Glass of water. Taking a pencil.
A regular graphite pencil.
And a sugar cube.
A regular sugar cube.
And all that, yeah, that should work. Oh,
my God.
I'm going to put the letter
Yeah, Dad.
A. So you can see there's an
Okay, so there's an A on the sugar cube.
A there. All right. Now, may I have your hand? Now you look at the
Okay,
hand.
now there's nothing on Seth's hand at all. It's going to be clear. Drop it in there, cover his hand.
Careful.
As the sugar cube dissolves, see what happens here.
And
You can't see it very well, but right there, the letter A has appeared on the hand. Is that a problem? Yes. Okay, so how did that take place? That's a problem. We made observations. We have water. We have pencil. We have a sugar cube. So what are some tests we could do? We could change out the water. We can replace it with alcohol. We could also maybe change out the pencil to a pen to see if that changes things. Instead of a sugar cube, we could do maybe a bouillon cube to see that. Those are different things that we could test in a scientific method to see if a theory, a hypothesis, maybe the pencil evaporates and comes up. Those are all theories that my students have suggested through the year. Now let me go to my next video and actually show what happened here.
but this time I'm going to do it very, very, very slowly.
So you can get all the details.
So
A little dad joke going in here.
Start with the letter A.
Now watch what happens as I put the sugar cube in the water. See my hand?
This is-
Watch my hand. There's no A there. Aha, did you see it? Did you see it? There's the A. All right. Now, what happened here is that was a magic trick. Wasn't chemistry at all. I need all of you. All of you right now listening, raise your right hand. The right hand, not the left one, the right hand. Repeat after me. I promise. Say it out loud. I promise. Under penalty of death or worse, never to disclose the secret of the sugar cube. That is the magician's code. You've been sworn in. You can't tell anybody. All right. Now, you had a bias. You had a problem, a bias. What is a bias? Bias is a preconceived idea that affects the outcomes of research. There's two examples of bias that I always give in my class. Back in the late early 1900s, there was a group of scientists who were looking for a missing link, evolution, from goo to you through the zoo. And they went to the island of Peking, and they found an ape head, and they found what looked like human arms and human bones, and they found, we got the missing link, and they called it Peking Man because it was found on the island of Peking. Several years later, after many of the scientists had died, they did research on it, and they found that it actually was an ape head, an orangutan, and human arms. They were just different bones in the same cave. Did the scientists do that on purpose? No, I don't personally believe that. I just think they got so focused on finding the missing link that they found one. They had a bias. Now, there's also an example of a research bias that was a little bit less than truthful. There was a scientist who was trying to find a gene to cause a certain behavior. And he said he found the gene. Everybody got all excited. One of the universities, I believe it was Stanford, tried to replicate it. And they went years and years and years and years and years, and I couldn't get it to work. So finally they called him up and said, Doctor, what's going on here? We're not able to replicate it. And he laughed. He said, you're not going to either. See, I lied. There is no gene. Okay? Now, is that bad? Yes. His rationale is you tell a lie often enough, people believe it. So, as a result, wasn't a good thing. Now, the way that we overcome both of these, both intentional and unintentional bias, is a peer review. It's a way of having others attempt to replicate or further study your findings. In the case of the Peking Man, they did testing on the bones. On the case of the gene, they looked at the findings and they found that they couldn't replicate it. So all of those are ways of the scientific method to identify it. So that is day one, scientific method. Tomorrow or the next day, we're going to look at significant figures and significant digits and then clean up from there. Hopefully this wasn't too bad for you. Take care. God bless.